Okay, in Chapter 7, we're going to be talking about systems of linear equations and matrices and stuff along those lines. Okay, let's start talking about Section 7.1, being systems of linear equations in just two unknowns or two variables. Okay, you've probably been exposed to this stuff before, so it shouldn't be altogether new. All right, let's get my little pen up here first. All right. Suppose that we wish to find values of x and y such that these values satisfy both of these following equations, okay? I've got two equations. I've got 3x minus 2y is 18, and I've got 5x plus 10y is negative 10. Okay, I want values of x and y that'll satisfy both these equations, not just one of them, both of them. Okay, we call a set of equations to be satisfied a system of equations. Okay, so this represents a system of equation, these two. And the system above is called linear because each term of each equation is of degree 1. Okay, that's of degree 1, that's of degree 1, that's of degree 1. In x, this is of degree 1 in y. Okay, so these are a system of linear equations. Okay? Now, geometrically, we could find any solutions to a system of linear equations, such as this, by graphing both of the equations in the xy plane, in which case we would obtain what? Two lines. If we were to graph this guy, we would get what? A line. If we were to graph that guy, the set of all values xy satisfying that condition, you guys know that that's a line also. So we would get two lines. Okay? And we'd be interested for a solution, quote unquote, we'd be interested in obtaining their point or points of intersection. Okay? So those would be what? Values of xy or points with coordinates xy lying on both lines. Okay? So in essence, geometrically, we're looking for the point or points of intersection of these two lines. Okay? Alrighty? I'll just mention here, we're going to be doing more linear equations and more unknowns. And let's start by saying this. This method, geometric method, does not generalize to system of equations with more than three variables, since we must graph in at most 3 dimensions, right? Okay, besides this fact, this method can be time-consuming if you're doing it by hand, without the use of computer graphing systems like Desmos or GeoGebra. Nevertheless, I will mention here the geometry of linear equations will give us insights into the possible nature of solution or solutions, which we will see later. Now let's move on to actually solving this system, okay? Okay, so back to the first example here. So I've written it again. The first method I'm going to talk about is something called the substitution method. So here I've got my system written again. 3x minus 2y is 18. 5x plus 10y is negative 10. Okay, in this so-called substitution method, we take one of the equations and solve for one of the variables, then use the expression for that variable in substitution in the other equation. Okay? All right, let's see this concretely. Okay? Now, it doesn't matter really which equation you use here, but I'm going to go ahead. It looks easier to me if I take the second equation, which is 5x plus 10y equals negative 10, and I'm going to go ahead and it looks easy to solve for x there. So I'm going to add negative 10y on each side, isolating the 5x, and then I'll divide both sides by 5. So we get what? X is actually equal to negative 2y minus 2. This is the same line as I've got above here. Okay? If you were to go on Desmos and graph these two lines, they'd be exactly the same two lines. Okay, I've just rewritten the first equation with x isolated or x solved for. Now, in our technique, okay, we use the second equation. So this is what I'm going to do in the first equation. In place of x here, I'm going to use this expression negative 2y minus 2. Okay, so we're going to go ahead and do this. Here is our first equation, 3x minus 2y equals 18. Now I'm going to substitute in for x there, okay, this expression. So you can see, don't forget your parentheses here when you do this, because that 3 as a multiplier is going to multiply in both of these terms here. So it's 3 times the quantity, negative 2y minus 2, and then subtract your 2y, and that gives you 18. Now the beauty of this is we now have a single equation in a single unknown, right? Okay, let's go ahead and simplify that expression on the left-hand side of that equation, and I got negative 8y minus 6, and that's still supposed to equal 18. Let's isolate y by adding 6 on each side, then dividing by negative 8, and I get 24 divided by negative 8, and I get that y must be negative 3. Okay, now when I find a solution to a system of linear equations, or any equations for that matter, nonlinear or linear, I want both the value of x and y, or x, y, and z, or whatever the unknowns are. So I also need my x value before I stop my problem here. So let's go ahead and back substitute to find x. You remember I had this expression up here, x in terms of y here. X is negative 2y minus 2. So I'm going to substitute. I found that y is actually negative 3. So I'm going to substitute that in there. So I go negative 2 times negative 3 minus 2, and I get x equals 4 if I did my arithmetic correctly. And we could write our solution then alphabetically. X is 4 and y is negative 3. Or sometimes people can write it as an ordered pair, 4, negative 3. You know, like points in the xy plane, like we were mentioning. This would imply that x is 4 and y is 3 also. Okay, you could consider this 4, negative 3 to be what? That's the coordinates of the point that these two lines up here, these two lines have in common. This is where they intersect. You could double check that by looking on Desmos if you wanted. Okay, it would be an easy task to graph those two and see where they intersect here. Desmos is really good for that. By the way, if I do have a solution to a system of equations, it's often a good idea to go ahead and check them. Okay, let's see. We had the what? 3x minus 2y. That'd be 3 times 4 minus 2 times negative 3. That would be 12, and 6 is 18. That's just exactly what I wanted, right? Looking at the original system here. 5x plus 10y, that'd be 5 times 4 plus 10 times negative 3. That'd be 20 minus 30, that's negative 10. That's also what I wanted. Okay, so it works. Okay, so we proved that the solution is 4, negative 3. And in fact, that's a unique solution. There's only one of them. Because these two lines are not parallel, they're actually going to intersect at a unique point. These two lines, I should say, up here. Okay? All right, let's come down here. Let's talk about our second method called elimination. Substitution method was really good for 2 equations and 2 unknowns. It doesn't generalize quite so easily here. We're going to talk about a second method called elimination, and this is going to generalize, and it's going to be something, well, in a slightly different form here. We're going to create something called Gaussian elimination, and we will be using that generally in many instances for many reasons. Anyways, okay, let's get into this. Okay, I've got 3x minus 2y equals 18 again. 5x plus 10y is negative 10. Okay, so this is the same system. I'm just illustrating the second method of solution. We better get 4 and negative 3 again, right? Okay, let's see what happens here. What is this technique? In this method, we multiply, and I should say, or divide. Now, when we divide, it's like multiplying by a reciprocal, so the word divide is actually complete here, comprehensive, but I will throw this in for the sake of completeness and for clarity for students here. So in this method, we multiply or divide. You could say one or both equations by non-zero constants. Okay, do not multiply by 0, and you certainly can't divide by 0. If you multiply by 0, you just get 0. Okay, so you're not going to be dealing with the 0 constant. Okay, we'll multiply one or both equations by non-zero constants. That means on both sides of the equation. And then we'll add or subtract the equations Okay, so we could add or subtract. Typically, we will be adding. Again, you would never actually need to subtract if you use the right constants here. Addition would always be possible. But anyways, we'll add or subtract the equation so as to eliminate one of the variables. Okay, this is where the term comes in, elimination. You want to eliminate one of the variables. Of course, the constant or constants that we must choose in multiplying or dividing up here must be appropriately chosen to affect this elimination. Okay, now this doesn't mean that there's a unique way to do it. There is infinitely many ways to do it, but you want to try to pick a technique that's nice and convenient here. Okay, now this is what I did. We'll come back. We're looking at this system here, right here. Now, what I looked at here, I thought about eliminating the y. That looks easy. Do you see if I multiply the first equation here on both sides by the constant 5, that I would actually get a negative 10y right there? Okay? So that's what I'm thinking here. So I took the first equation and I multiplied it by 5, and I would get what? Don't forget the distributive property. It's going to multiply on every term. So this is 15x minus 10y. 5 times 18 turns out to be 90. So this is an equivalent line. That's the same line. It's just written in, what, a different form. Okay? And then I kept my second equation. I didn't change that one. That was 5x. That doesn't look like 5. That's because I wrote it incorrectly first. But that's actually 5x plus 10y equals negative 10. Now, notice that I've got something nice happening here. If I just add these two equations, equals added to equals should still be equal. Now, I'm just going to add these in columns conveniently. So 15x plus 5x gives me 20x over on the left-hand side. Here's where the nice part came in, where you get the elimination. Negative 10y plus 10y gives you 0y. 0 times y is 0, so I'm not going to add anything or subtract anything from the 20x, right? It's just imagine it eliminated. It's gone. Okay? Remember, we're adding here, so 90 plus negative 10 is like 90 minus 10, so that's 80. Divide on both sides by 20 to isolate your x value. X is 4. Now you can back substitute x equals 4 into either of the original equations, and you will find, I used the first equation, and with x equals 4, and you will find once again that y is negative 3. So we got the same solution that we did in the previous substitution method, right? Okay, we found the same solution. We better have. Okay, alrighty. So there's an elimination method. Okay, I want to talk a little bit about the nature of solutions to a system of linear equations. Notice that I made that capital here, linear equations. Okay, so what I'm saying in the following applies only to systems of linear equations, okay? Linear equations have what? Every term in the equation is of first degree, okay? Or constant, I should say. I guess I should have said that up there, constant, which means, okay, 0 degree or first degree. Okay, in a system of two linear equations and two unknowns, we can think of any solution, as I stated above, as a point in the xy plane that lies on both lines represented by the equations. Okay, how many possible solutions are there in such a scenario? Okay, there's actually 3 possibilities. Okay, so I'm thinking about the intersection of two lines. You could have a unique solution. This is where the two lines intersect at a single point. Okay, you can imagine that in your mind. In the xy plane, we're not talking about 3 dimensions, just in the plane. Okay, the two lines could intersect at a single point, and that would correspond to a unique or one solution. There are no solutions. Imagine that the two lines are parallel, but distinct. Okay, parallel lines. Parallel lines never intersect, right? There's not going to be any points in common, so there would be no solutions. Okay, no real solutions. Okay, or there could be infinitely many solutions. Suppose the lines are actually identical. Okay, just written in a funny way so they look different, but they're actually, the system boils down to a single line. Now I'm talking about just two equations, two linear equations and two unknowns at this point. Hope we're going to see something here. Okay, although we've only considered two equations and two unknowns as our system above, in fact, any linear system, no matter how many equations, again, linear, this is important. Any linear system, no matter how many equations or unknowns, will manifest one of the three possibilities listed above. In other words, if I've got any linear system, there's either what? One solution, no solution, or infinitely many solutions. Now we're going to see that in greater depth when we get to the next section, which is going to be called Gaussian elimination. By the way, I'm not following the order of the book. I don't like the order in which they put things, but there it is. Okay, now just quickly, let's take examples of each of the types of behavior that we've got above as far as solutions go. A unique solution exists. Well, I'm not going to do that again. See example 1. Okay, remember the example where the x equals 4 and y equals -3? That was what? The only point in common between these two lines. Okay, they intersected at a unique point. Okay, no solution exists. This is really easy. Okay, I'll call that example 2. Suppose I have my following system looking like this. X plus y is 3 and x plus y is -5. Okay, obviously there exists no pair of values here, real values x and y, such that when we add them, right, x plus y, we get both 3 and -5. Okay, so there is no solution. If we were to graph these on Desmos, we would in fact see that we've actually got a pair of parallel lines. Okay, these two lines actually have a slope of -1, but they have different y-intercepts. They're actually parallel lines. Okay, so no points in common, no solutions to the system. Okay, last example here, we'll call this example 3. I guess I didn't write it that way, but that's fine. Example 3. We've got the following system here. We've got x plus y is 3, and then we've got 2x plus 2y is 6. Aha! I think you can see very clearly that the second equation is found from the first equation by just multiplying on both sides by 2, or doubling each side. Okay, if I multiply by 2 on the left, I would get 2x plus 2y. If I doubled on the right, I would get 6. That's exactly what I have here. Okay, if you were to graph both of these on Desmos, you would find the second line is exactly the same as the first line. Okay, so the second line would actually be redundant here. It's really adding nothing to the system. The only values of x and y common between the two are the set of all values x and y that lie on that first line, which is the same as the second line. So the xy is a set of all points on the line x plus y equals 3, where there's obviously infinitely many points x and y whose sum is 3, right? Okay, those are all the points on that line. Okay, so the word is redundant that I used on this one. Later they will be using the term dependent, okay? But this is where you have more equations and more unknowns. Then it won't be so obvious when you have infinitely many solutions. And when you're talking about 2 equations and 2 unknowns, it's usually super easy to see if you have no solutions or infinitely many solutions. Okay? Alrighty. Well, I hope you understood all this. This is probably review for you. We'll get into Gaussian elimination next, and hopefully you'll listen to that soon enough. Okay? Go ahead and work those problems that I've assigned.